All right, so today we're going deep on something that might seem kind of basic at first,
Yeah.
the anode.
Right.
But as we dig into Jorgo Schneppat's essay, Anode, Schlüsselkomponente in der Quantentechnology,
Yeah.
we'll see why it's actually this hidden powerhouse driving all kinds of quantum tech.
You know, it's funny how a component that's so fundamental can be so easy to overlook.
Yeah,
Schneppat really shines a light on that.
totally.
Showing how crucial the anode is in both classical and quantum electronics.
Absolutely. But before we go full quantum, let's make sure we're all on the same page.
Okay.
Can you remind us, what exactly is an anode?
Well, in the simplest terms, an anode is an electrode.
Okay.
Where oxidation happens. It's basically the spot where electrons get lost during a chemical reaction.
Okay.
Think of it like, it's like the electron's launch pad, sending them off to do work.
That makes sense.
Yeah.
And Schneppat's really clear that we can't talk about anodes without talking about their counterpart,
Right.
the cathode.
Exactly. They always come as a pair. An anode and cathode work together to create that flow of electrons.
Right.
Like, think of a battery.
Yeah.
The negative terminal, that's your anode.
Okay.
It's where the electrons are released.
Right.
And then the positive terminal, that's the cathode, where they're drawn back to.
I see. So
It's a constant push and pull, with the anode really kickstarting the whole thing.
so this tiny component is kind of orchestrating the flow of energy in so many devices.
Yeah, pretty much.
That's amazing.
It is.
But I'm guessing it's not just about batteries, right? Schneppat takes us way beyond that, I imagine.
Oh, absolutely. He gets into how anodes are essential in all sorts of electronics.
Okay.
From the classic stuff like diodes and vacuum tubes.
Yeah, the old tech.
Right, all the way to the cutting edge quantum devices.
Okay, now that's where I get really interested.
Yeah.
So how does this little electrode step up to the challenges of quantum technology?
Well, one of the most exciting areas is quantum sensing.
Okay.
You know, those incredibly sensitive detectors that can pick up the faintest signals.
Right.
Like single photons or super weak magnetic fields. Anodes are crucial there.
How so?
They act as these collection points for the electrons generated by those signals.
So they're basically gathering all those tiny bits of information the sensor's picking up.
Exactly. They're like the gatekeepers, making sure those precious signals are captured and turned into data we can use.
Wow. So they're essential for those super sensitive measurements.
Totally.
That's remarkable.
It is.
And what about quantum computing? That always feels like something out of science fiction.
Yeah.
Where do anodes fit into that?
Well, Schneppat focuses on two main areas there.
Okay.
Superconducting qubits and ion traps.
All right, let's break those down.
Okay.
So in superconducting qubits, those tiny circuits that hold quantum information,
Right.
anodes are part of something called Josephson junctions. Right?
Yes.
Now, those sound familiar, but definitely need some explaining.
Okay, sure.
So what are Josephson junctions, and how do anodes come into play?
Imagine two superconductors
Right.
separated by a tiny insulating barrier.
Got it.
That's your Josephson junction.
All right.
Now, because of how quantum mechanics works, electrons can tunnel through this barrier,
Right.
and the anode is crucial in controlling this tunneling process.
I see.
Which is how we manipulate the qubit's state and make those computations happen.
So it's helping us harness the power of quantum tunneling to make those qubits work.
Exactly. It's a great example of how we're taking classical electronic principles, like those we see in diodes,
Right.
and applying them at the quantum level to control individual electrons.
That's amazing.
Right.
And what about ion traps?
Right?
I know those are another type of quantum computer, but how do anodes work there?
Well, with ion traps, we're using individual ions,
Oh, yeah.
charged atoms, to hold that quantum information.
Okay.
Anodes are crucial for creating the electric fields that trap these ions.
I see.
So they keep them stable and isolated so we can then manipulate their quantum states.
So the anode is like a tiny force field, holding those quantum bits in place.
You got it. And that control is absolutely essential to do those quantum computations.
This is all fascinating. We've gone from batteries to quantum tunneling to ion traps.
It's a wild ride, right?
It is.
Yeah.
But I know there's more to this story.
Yeah.
Especially when it comes to those more out there applications Schneppat mentions, like quantum communication.
Absolutely. And that's where we'll pick up next time, exploring how the anode helps unlock secure communication using those bizarre rules of quantum mechanics.
Awesome. Looking forward to it.
Me too.
So we're back, diving deeper into the world of the anode and its surprisingly big role in quantum tech. Before we jumped off, we were just starting to talk about quantum communication.
Right, and it's a really interesting area where the anode's contribution is subtle, but super important. Schneppat really highlights that in his essay.
Okay, so paint the picture for us. How does quantum communication actually work? And where does our trusty anode come in?
Imagine sending messages that are like fundamentally unhackable. That's the promise of quantum communication.
Okay.
It all comes down to quantum mechanics, where information gets encoded in the state of individual photons. You know, those tiny particles of light.
Right, so we're using light to transmit information.
Yeah.
But at this, quantum level, that sounds crazy complex.
It definitely is. And a big challenge is being able to detect those single photons reliably. That's where the anode steps in. Schneppat explains how single photon detectors, which are absolutely key for quantum communication, rely on anodes to amplify those incredibly faint signals.
So the anode is like a signal booster for these quantum messages.
You got it. It makes sure that even the tiniest whisper of a quantum signal gets picked up loud and clear.
Right.
And these detectors are super important for something called quantum key distribution, or QKD. It's a way to create encryption keys that are basically unbreakable.
Unbreakable encryption. That's like straight out of a spy movie.
I know, right?
So we're talking about security that even the best hackers can't crack.
Exactly. It's all thanks to the weirdness of quantum mechanics and the anode's ability to detect those single photons.
This is blowing my mind. So if anodes are so important in all these quantum technologies, are there specific materials that work best? Or are we still just using the same old anodes from batteries?
That's a great question. Schneppat digs into that in his essay. Choosing the right anode material is crucial for quantum systems, and it all depends on the specific application and what kind of performance you need.
Okay, so break it down for us. What kind of materials are we talking about here? Is it a whole different world from what we see in, everyday electronics?
Schneppat talks about three main types: superconducting materials, semiconductors, and metals.
Gotcha.
Each has its own pros and cons when it comes to quantum stuff.
Okay, well, let's start with superconductors.
Sure.
I know they're the cool kids in quantum tech.
Right.
What makes them so special for anodes?
Well, superconductors can conduct electricity with zero resistance below a certain temperature. Okay. This makes them super efficient. No energy wasted as heat.
Right.
Which is really important for those delicate quantum systems.
So no energy loss. That's a big win for these quantum devices.
Totally. And Schneppat mentions some of the stars of the show in the superconducting world, like niobium, which is often used in those Josephson junctions for superconducting qubits we talked about.
Right, yeah.
And niobium titanium, a workhorse for making strong magnetic fields used in quantum sensors.
Niobium titanium. These are not your everyday battery materials. But I'm guessing there's got to be a catch. Superconductors aren't a magic solution, right?
You're right, there are always trade-offs. The main challenge with superconductors is they need to be kept super cold, often just a few degrees above absolute zero. That's colder than space.
Wow.
And getting that level of cryogenic cooling can be tricky and expensive.
So cryocooling is a must. But even with that, it seems like superconductors are still a top choice for quantum anodes.
Yeah, for sure.
What about semiconductors? Where do those fit into the picture?
Semiconductors are super important for modern electronics in general.
Yeah.
And they also play a big part in certain types of quantum devices.
Okay.
Schneppat points to silicon as a common choice for anodes in these systems.
Silicon. That's what's in our computer chips?
Exactly. Silicon's really versatile.
Uh-huh.
It can be used to make quantum dots.
Okay.
These tiny semiconductor nanocrystals that track electrons and show those quantum properties.
Wow.
It's also used in some single photon detectors.
So even familiar materials like silicon have a role to play in this quantum world.
Right.
Does Schneppat mention any other semiconductors that stand out?
Yeah, he talks about gallium arsenide.
Okay.
It's another important one that's particularly good for quantum devices that use light.
Interesting.
You know, things like quantum LEDs or single photon sources. It's very good at converting electricity into light and vice versa.
So it's like a bridge between electronics and photonics, the science of light.
Exactly.
And of course, we can't forget graphene,
right?
The wonder material everyone's talking about.
It's everywhere these days.
It is. Just a single layer of carbon atoms.
Yeah.
Arranged in a honeycomb lattice.
It's incredible.
Incredible electrical and mechanical properties.
Makes it a really strong contender for future quantum tech.
Graphene always seems to be making headlines.
For good reason.
So we've got superconductors, semiconductors, all these high-tech materials. But what about good old-fashioned metals? Do they still have a place in quantum anodes?
Absolutely. Metals are still super relevant.
Okay.
They're great at conducting electricity, which is what we want in an anode. Gold, for example, is often used for contacts in quantum chips because it's so conductive and doesn't corrode easily.
Gold. Not just for jewelry anymore. What about other metals?
Well, copper's another common one.
Right, in electronics.
It's used in quantum systems, too, often as a base layer for superconducting chips. And then there's platinum, sometimes used in quantum sensors because it's so chemically stable.
So metals are holding their own in the quantum world. But I'm sensing a but coming.
Yeah, you're right.
Are there any downsides to using metals for anodes in these sensitive quantum systems?
The main issue is that metals do have some resistance, even though it's way lower than insulators. So that means they generate some heat when current flows through them.
And heat's not a good thing when we're talking about quantum devices that need to be super cold, right?
Exactly. Those energy losses due to resistance, we call them ohmic losses, can be a problem in these systems. They can mess with the delicate quantum states and make the device less efficient overall.
So it's this balancing act between wanting good conductivity and minimizing energy loss. It sounds like picking the right anode material is a tricky business.
It is, and Schneeppert really emphasizes that. He talks about how scientists are turning to nanotechnology to engineer materials with very specific properties to address these challenges.
Nanotechnology, now we're talking. Shrinking things down to the atomic level, right?
Precisely. Nanotechnology lets scientists manipulate materials at the nanoscale, creating structures that can do things their bulk counterparts can't. It's like giving an already great material a quantum upgrade.
I love the sound of quantum upgrades. What are some examples of how nanotechnology is improving anodes?
Well, Schneeppert talks about the potential of graphene nanostructures.
Okay, graphene again.
Yeah, it's a big deal. By crafting these nanostructures just right, scientists can boost graphene's already amazing conductivity and reduce those energy losses.
So we're making an already powerful material even better.
Exactly. And another cool area he mentions is using superconducting nanostructures for anodes.
Okay.
These tiny structures have unique quantum properties that can be used to make quantum devices even better.
It sounds like we're entering a whole new era of material science.
Yeah.
Where we're not just using materials as they are, but engineering them atom by atom to meet the needs of quantum technology.
It's a really exciting time to be working in this field. But as with any new technology, there are still hurdles to overcome.
I was just thinking that. All this talk of superconducting nanostructures and graphene makes it sound like we've got it all figured out. But I'm guessing there are still challenges ahead.
You're absolutely right. Schneeppert brings up a crucial point. Material stability, especially under the extreme conditions that many of these quantum devices need, is a big challenge.
Okay, let's dive into those challenges because I have a feeling they're not easy to solve. What are we up against when it comes to keeping these quantum anodes stable and reliable? Okay, so we're back and we've been exploring how the anode, this tiny component, is actually playing a huge role in the future of quantum technology. But as we've learned, keeping these quantum anodes stable and working reliably, that's a whole other challenge.
Yeah, it's a constant battle, especially when you're working at the quantum level. Schneeppert doesn't sugarcoat that in his essay.
Before we left off, you mentioned material stability as a big hurdle. What makes it so hard to keep these quantum anodes stable and reliable?
Well, think about it. A lot of these quantum devices need to operate in some pretty extreme environments.
Right, like those cryogenic temperatures we were talking about.
Exactly, just a hair above absolute zero.
Yeah, colder than space.
And at those temperatures, even the tiniest impurity can cause a big problem.
Really?
Yeah, a superconducting material could suddenly lose its superconductivity if there's even a trace amount of certain contaminants.
Wow, so it's all about maintaining this super delicate quantum state.
Exactly. And then there's thermal stress, too. When materials go through these huge temperature swings, they expand and contract, which puts a lot of stress on them. Over time, that can lead to damage or even complete failure.
So building a stable anode for these quantum systems, that's like a high-stakes engineering challenge.
It definitely is. And it's not just the extreme temperatures. There's also the constant threat of contamination.
Contamination? You mean like dust and dirt getting into these sensitive devices?
Well, yeah, but think smaller. We're talking about contamination at the atomic level. Even tiny particles can mess with those delicate quantum states.
Wow, so keeping things clean is a whole different ballgame here.
Oh, yeah. So for metals, even something as basic as oxygen can be a problem. If a metal anode oxidizes even a little bit, it can increase the resistance and lead to those energy losses we talked about.
Right, so it's like a microscopic battle against rust.
Pretty much. And then in semiconductors, you've got to worry about uncontrolled doping. If those impurities aren't carefully controlled, they can create unwanted electrical pathways and mess up the device's performance.
So it's like we're trying to control these materials at the atomic level, making sure every atom is exactly where it needs to be.
Precisely. But it's not all doom and gloom. Schneppat talks about how scientists are coming up with all these ingenious ways to fight these challenges.
Okay, good. So what strategies are they using to protect these quantum anodes?
One approach is all about creating ultra-controlled environments, like using ultra-high vacuum chambers where almost all the air molecules are removed,
right,
and those cryogenic cooling systems.
So it's like building a fortress of purity for these quantum components.
Exactly. It's all about minimizing any outside disturbances that could mess up the quantum balance. And then there are techniques like ion beam etching,
right,
which is used to remove unwanted material with incredible precision down to the atomic level. It's like a microscopic scalpel.
Wow, that's amazing. What else are they doing?
Schneppat also mentions chemical passivation,
okay,
which is basically creating a protective layer on the anode's surface to stop contamination. It's like a suit of armor for the anode.
So scientists are pulling out all the stops to protect these tiny but powerful components.
They are. And Schneppat wraps up his essay by saying all this research into materials, science, and nanotechnology is paving the way for even more stable and reliable quantum devices in the future.
This has been such a fascinating journey. We started with a basic definition of an anode, and now we've explored its essential role in the incredible world of quantum technology. It's amazing to think that this little component is driving so much innovation, and scientists are tackling some truly mind-blowing challenges to unlock its full potential.
It really highlights how something as seemingly simple as an anode is actually at the forefront of this quantum revolution. And Jörg Schneppat's essay does a fantastic job of bringing this often overlooked aspect to light.
A huge thank you to Schneppat for his insightful essay. And to everyone listening, as we keep pushing the boundaries of quantum technology, what new discoveries await us in the world of anodes? Keep exploring, keep questioning, and keep diving deep.